for the introduction. And again, yeah, it's Friday, especially Friday afternoon seminar. Good chance to unwind and talk about some science and engineering. Feel free to stop me at any point and ask questions. And I also welcome ideas and thoughts about where we could take this technology moving forward. This is a brand new technology. We reported on it for the first time this past January. So we are definitely in a phase where we're thinking about where to invest resources in moving forward and what are some of the low-hanging fruit research questions that could be asked. So I'm excited to be here among EEs and EBEs. So again, as Daniel said, you're not interrupting. I would prefer to have a discussion, especially in this setting, rather than lecture at you. Especially because I think some of you may have heard some of this material already. I'm going to talk about computer-designed organisms today, and I had 3 collaborators on this work, one of whom was Sam Kriegman, my PhD student here. Sam was here earlier in your seminar series, and I spoke briefly with Sam about what aspect of computer-designed organisms he presented. So I pulled together some material that is sort of the all of the supporting technologies and ideas that went into the xenobots. So I'm not going to talk too much about the xenobots directly today. I'll talk about them briefly for the first few minutes just to refresh your memory and sort of set the stage. If you do want to hear more about the xenobots directly, again, feel free to stop me and ask questions, and we can dig down into the xenobots themselves. Otherwise, I will talk a little bit about sort of the philosophical and some of the computational infrastructure that led up to and supports xenobots, which are their nicknames, but more formally known as computer-designed organisms. Okay, so I worked with Sam on this project. Sam just successfully defended his PhD thesis this semester, and we teamed up with 2 biologists at Tufts. Michael Levin runs the Allen Institute of Regenerative Biology at Tufts, looking at how organisms are able to maintain form and function, not only over their lifetimes, but as they suffer unexpected situations like grievous injury, and especially organisms that have the ability to grow back lost structure. And that's something we look at in robotics. So I'll talk a little bit about that, how that collaboration came to be a little bit later. Doug Blackiston is a research scientist in Mike's group at Tufts, and Doug is a microsurgeon. Very accomplished microsurgeon, never drinks coffee, never drinks Coke, no caffeine, has very fine motor control. And in this particular project, he was able to take some of the blueprints that our machine learning method generated, our evolutionary algorithm, which designed the virtual xenobot you see on the left. And Doug was able to gradually build up the xenobot out of frog epithelial or skin cells, which are shown in green here, and frog heart muscle tissue, which is shown in red here. So on the surface, I think part of the reason why there was a lot of media attention on this project is it's something that's relatively easy to understand. On the left, you have an AI that is automatically designing virtual creatures. And then on the right, we built those robots out of frog cells following the AI-generated set of blueprints. However, like most science and engineering efforts, there's a lot of the devil's in the details, a lot of stuff under the hood. So I'm going to focus on some of that today. Okay, any questions, comments? Okay, so just for reference, we're going to be talking about these little guys today, and there's Sam holding up a plate, and you can see one of the xenobots there, which is sub-millimeter in diameter, so about the size of a grain of sand. That's the size scale that we're working at. Okay, so just to walk you through how this project works, we start with an evolutionary algorithm. Which is a very simple machine learning method, at least on the surface. And the basic idea in all evolutionary algorithms, and there are many, many different kinds of evolutionary algorithms, but one thing they all share in common is they start and maintain a population of hopefully diverse solutions to your given problem. The other nice thing about evolutionary algorithms is they're domain agnostic. You can apply them to frog bots like you see here. They've been applied in hundreds or thousands of different branches of engineering and science and architecture and design and so on. In this case, we connected our evolutionary algorithm to a particular finite element soft body simulator developed by our colleagues at Columbia. This is known as VoxCAD. If you Google VoxCAD, just type it into chat here. If you Google VoxCAD, you can have a look and download this and play around with it if you like. So our evolutionary algorithm is going to take a series of designs and instantiate them in VoxCAD. Here's the beginning of one run of this evolutionary algorithm that's created one random design. There are various inputs that you need to supply to the evolutionary algorithm. The first one is to supply it with the building blocks. What are the atomic elements from which it can build its machine or design? In this case, we told the evolutionary algorithm that it has available cyan voxels, or 3D pixels, volumetric pixels, voxels. Cyan voxels, which are passive and soft, so they will passively deform when pulled on by neighboring voxels. And red voxels, which are controlled by an open loop controller, just a sinusoidal pattern that we supply to each of the red voxels, and that pattern expands or contracts the volume of the red voxels. You also need to supply a fitness function or a loss function or an error function, which basically just tells the computer how to measure the quality of any given design. In this case, we wanted to evolve xenobots that were able to move as quickly as possible. So the fitness of any one design is its displacement from the origin over a fixed time period. You can see that this initially random design doesn't displace at all. You'll notice also in the case of the red voxels that they're expanding and contracting in random phase offsets from one another. So as I mentioned before, from the evolutionary algorithm's point of view, these are just passive or open loop controlled voxels. When we instantiate them in reality, the cyan voxels are going to become passive epithelial frog cells, and the red voxels are going to be heart muscle tissue. If you take frog heart muscle tissue and put it together in the shape of an adult frog heart, that tissue will spontaneously synchronize, which is a good thing because you want the heart to act as a pump, and it will, the heart as a whole will expand and contract. Turns out that if you rearrange heart muscle tissue and put it together, it will still spontaneously beat, but it won't necessarily synchronize. And it is not currently known for a given rearrangement of heart muscle tissue what sort of phase dynamics you will get in that hunk of tissue. So in the lack of better knowledge of that, we built in a very conservative estimate, which is just that the phase offsets are going to be random. So this makes a very difficult engineering design problem because we are in essence asking the evolutionary algorithm to evolve or design a machine that produces a non-random behavior, straight and rapid movement. But at least one of the two basic parts, we're going to assume that an important part of its function is random. Here's one random design. Here's another random design that the evolutionary algorithm produced. In this case, it's all heart muscle tissue. And again, the second random design doesn't displace noticeably from the origin. Here's a third random design. So this just gives you a sense for sort of where the evolutionary algorithm starts. So basically, this is a needle in the haystack problem. There are very, very few good solutions. But as you probably know, or you can even guess from the name, this evolutionary algorithm assigns a single number to each individual, which is fitness. Those that have low fitness, that are slow movers or no movers, are deleted. And the survivors, we then make copies of these designs and introduce random mistakes so that the child robots are similar to but not identical to their parents. There's a course here at UVM that I think will be taught by Nick Cheney next semester called Evolutionary Algorithms, where you can see some of this work at play. I also teach Evolutionary Robotics next semester, where we go into this idea in a fair bit of detail. If you repeat this, yes.
Question. Yeah, this
Sure.
is Jason Bates.
Hi, Jason.
Hi. If you put heart cells together, I mean, they may, in a sense, start off beating randomly, but the way it works in a heart is that one will entrain the next. They entrain each other. So they don't act independently normally, even if they're, I suspect, in the wrong order. So do you keep these things beating randomly, or do you allow entrainment?
We allow entrainment, but at least at the sub-millimeter scale with the frog heart muscle tissue that we were using, our microsurgeon, Doug Blackiston, was not convinced that they were all entraining with one another. He saw local patches that would entrain, but not an entire patch. So,
well, it requires that they are electrically connected. So maybe they weren't when you build them up.
That's the other thing, is that remember that he's building this by hand at the sub-millimeter scale. So he doesn't have a lot of fine control over the distribution of heart muscle and epithelial tissue. So we give him basically this design, and he builds something like this, but it's not perfectly what was dictated. So you probably can get, non-contiguous patches and all sorts of other messy details that means you can't guarantee that you're going to get entrainment in all the heart muscle tissue.
Got it. That makes sense. Thanks.
Yeah, no worries. No worries. Okay. So, however, despite the difficulty of this task, if you repeat this evolutionary algorithm for hundreds or thousands of generations, and you get something like this. This was the best design we were able to produce, or the evolutionary algorithm was able to produce in simulation. You can see that it places heart muscle tissue on the ventral or the bottom surface of this little xenobot, and the passive skin cell on the dorsal or top surface is somehow damping out our assumptions about non-entrainment, the random phase offset. So in a way, the distribution of tissue here and the 3D shape of the xenobot itself is collectively de-randomizing the random action of parts of the body. So you get a more or less straight line of travel from left to right. And in this case, at least, when Doug built this design under the microscope, he got this xenobot, which again doesn't look exactly like the evolved design, but close enough that it has more or less the right mass distribution and the right distribution of heart and skin, that we get more or less in reality what the evolutionary algorithm predicted we would get. As you can imagine,
Professor, sorry.
Yeah, Daniel, go ahead.
Yeah. Professor, I just wanted to, I think you might have mentioned it, I might have forgotten. The green part of that is the phase offset, isn't it, when you play the video?
Yeah, that's right. I'm sorry, I said red voxels, but once the red voxels are turned on, red and green represents, it doesn't represent phase, it's volume. So red voxels, I think, should be a little bit bigger, and green voxels a little bit smaller.
Okay. Yeah. Thank you, Professor.
Yeah, exactly. So again, this was a successful transferal from simulation to reality, and a lot of the designs do not transfer. This is known as the sim to real problem, and it exists in traditional robots, not just the biobots that you see here. This is an open problem in robotics. How do you guarantee that that an AI-derived solution in simulation will transfer to reality? Especially when you're using an evolutionary algorithm. An evolutionary algorithm, like biological evolution, will exploit whatever materials you make available to it, including approximations and errors in your simulation. So this is one big issue about trying to use simulation, is that often it will exploit these inaccuracies that work in the necessarily approximate model of the real world. And because they rely on those details of the simulation, when you transfer them to reality, the plant or the robot does not do what you expect it to do. One of the things that we're working on now, which I can't talk about too much because this hasn't been published yet, but that the basic idea is to draw observations from failed deployments. When a simulated design fail, or when the physical xenobot fails to act in the way that the simulated xenobot does, can you take the difference between the predictions from simulation and reality and use that error signature to work backwards to where in the simulation, or what is being exploited in the simulation that caused that failed sim to real transfer? So that idea is real to sim, and obviously this is something that engineers do all the time anyways. So for those of you that have ideas about how to automatically distill insight from reality and build it back into our simulated model, I would love to chat about that today or offline. Just let me know. Okay, I'm going to switch and sort of talk about where the idea for this project came from, but I'm happy to answer any other questions about the xenobots themselves, if anybody has any. So far, so good. Okay, so obviously this work lies at the intersection of AI and synthetic biology, and both of those fields are exploding at the moment. And this is one of many examples of where AI and synthetic biology meet. But it's interesting to think about why it's taken so long for this to occur. In the case of synthetic biology, it's because our ability to manipulate biological tissue has taken a while to catch up to the point where we can actually start to direct an AI to manipulate biological tissue. But this is sort of, from the AI perspective, this work kind of lies in this odd, underexplored branch of artificial intelligence, this idea of automatically designing machines with an evolutionary algorithm. And I wanted to talk a little bit about why that subfield is so small and often overlooked in the greater AI community. And in order to illustrate this idea, I'm going to use a visual metaphor here to talk about sort of the state of play of AI in general and where this approach of evolving machines lies in the AI landscape. So imagine we have one dimension here where if you take a given AI algorithm that is training a series of agents, that algorithm can be represented as a line segment embedded in this one dimension. This AI algorithm could be anything, and the agents or the things that it's being trained could be anything. They could be deep neural networks, they could be drones, they could be frog bots, doesn't really matter for our purposes. If you then imagine in that line segment, in that AI algorithm, as it's training agents that are increasingly performant at whatever we want them to do, the individual points in the line segment represent those agents. So for the last 70 years that people have been working on AI, give or take, we made very limited progress. Most AI algorithms that were proposed, from fuzzy logic to expert systems, case-based reasoning, all these other algorithms, they mostly hugged the left-hand side, or the origin, if you like, of this dimension. They weren't able to produce agents that did better than chance in a lot of situations. Thanks to the big data revolution and the deep learning revolution, there were some algorithmic innovations. Now we can, in many domains, we can produce deep networks that do better, that do as well, if not better, than humans. Those are AI algorithms or line segments that hug the right-hand side of this dimension. However, what AI is not so good at doing at the moment is producing general purpose machines that can do well at more than one task. So to extend this metaphor, imagine we add a second dimension here where each horizontal line, the height of each horizontal line represents a particular task, and the further up vertically that line is, the more difficult that task is from the point of view of current state-of-the-art AI. So checkers was solved early on, chess was quote-unquote solved a few years back, Go was quote-unquote solved a couple years ago, computer vision is almost solved, natural language processing still not very good. Each of these individual tasks has been better or worsely tackled by AI. If you now imagine an AI algorithm that is some kind of diagonal in this two-dimensional space, then the points that lie along this diagonal represent agents that are getting better and better at not just one task, but getting better at a growing number of tasks. A lot of state-of-the-art AI at the moment starts by training a learner on one task, and when the learner gets good at that task, it gradually exposes the learner to a second, then a third, then a fourth task. And I've drawn this line in red because those algorithms at the moment don't work very well. There's an open problem in AI known as catastrophic forgetting or catastrophic interference, which is that if you train an agent to do well at one or a few tasks and then expose it to new tasks, it will start to get better at those new tasks at the same rate that it forgets how to perform the old tasks. Very difficult to add a new behavior to a drone or a neural network and have it be able to retain other basic behaviors. This is an open problem. A lot of fascinating research going on in that area at the moment. A lot of people in AI just feel that with a few more algorithmic innovations and just more training data and more compute, we'll eventually solve the catastrophic interference problem and be able to train increasingly performant machines and increasingly general purpose machines. And some dreamers believe that this will eventually get us to artificial general intelligence. Nobody knows whether they're right or not. But a lot of roboticists tend to think about a third dimension, which is this concept of embodiment. So now we're dealing with a three-dimensional volume where points that are moving from the front face of this cube towards the back face of this cube are increasingly embodied. Embodiment is a term that comes from philosophy, and it means a lot of different things to a lot of different people. For our purposes, we'll just assume that embodiment means a richer or more complicated physical structure. So a physical machine that has more mechanical degrees of freedom. It's got more sensors. In the case of the xenobots, it's got more heart muscle tissue, more sense organs, what have you. So I've been working in this field for a long time, which is this idea of evolutionary robotics, where the evolutionary algorithm is an AI algorithm that is trying to move along this grand diagonal. The evolutionary algorithm is trying to produce machines that are more performant. They do better and better at the fitness function, or better and better at the loss function, if you like. We may be exposing those machines to more tasks, moving up the vertical axis. But most importantly, during the execution of this evolutionary algorithm, we are also allowing the EA to modify the physical structure of the machine. And there's lots of different ways it may modify the structure. It may add or remove motors, add and remove sensors. It may add elements to a swarm of machines if we're talking about swarm robotics. There are very, very few people today in AI that are working on methods that move along this grand diagonal. Personally, I believe this is the way, maybe not to AGI, but at least towards general purpose machines that can adapt their mode of operation as the world around them changes, and they can hopefully do more than one thing. So that idea, actually, I'm just going to skip ahead a little bit here, has been around for quite a while. So going all the way back to the early 1990s, a computer graphics researcher named Carl Sims made his own physics engine, applied it, ran it on the Connection Machine 5, one of the very first parallel supercomputers, and evolved some of the creatures that you see here. And this is still one of the high watermarks in our field. It's very difficult, even with modern technologies, to achieve what Carl was able to achieve in the early 1990s. 6 years later, Hod Lipson and Jordan Pollock connected this Sims method of evolving virtual creatures to a brand new technology known as 3D printers. And Hod and Jordan were one of the first ones to use 3D printers in an academic setting, where at that time the 3D printer was simply depositing thermoplastic, which is the white the white truss that you see here. And obviously they were 3D printing some of these evolved designs from simulation. And at that time, these were single material 3D printers. So they were snapping in the motors and sensors and electronics at that time. But this was an interesting demonstration of evolutionary algorithms that were successfully crossing the sim to real gap. I'll just pause for a moment. Any other questions, comments? No? Okay.
Yes, Josh, can I ask you a question?
Sure.
Hamid here.
Yep.
Is there a way to know the limit of performance when it comes to these artificial machines? For example, if the physics are given and if you know the number of these voxels,
yep,
how fast, like what is the limit? What is the best case?
Best case in what sense? You mean the computational?
No, in the sense of going from point A to point B the fastest.
Oh, yeah, exactly. So if we are assuming that the AI method can alter the physical structure, there is no known method that can guarantee convergence to the optimal solution. You do not know, by definition, what the optimal solution is. That is why you would use an evolutionary algorithm. If you fix the morphology, if you fix the embodiment, and you feel confident that you picked the appropriate physical structure, then there are, of course, gradient descent methods and other optimization methods that if they can't guarantee optimal convergence to optimal control policy, they can get you closer than an evolutionary algorithm. Evolutionary algorithm is better when we're assuming it is this sort of open-ended design space.
Mm-hmm. Okay, very interesting.
So if this is Luis Dufo. So if so basically I can get stuck on some minimum, right? And but so and if I get stuck into that minimum, so
what do you do?
So what do you do there, right? So because
yes.
So I'm
exactly. So you can constrain the problem, right, by simplifying or presupposing the physical structure, and you can do so with enough assumptions and enough constraints. You can assure that there are no local optima, right? You can translate this into a convex optimization problem. But in my experience, often you're throwing out the baby with the bathwater. You as a human engineer may make simplifying assumptions that evolution doesn't need to make, and may in some cases come up with non-intuitive but more elegant solutions than a human-driven approach would do. The cost, of course, like you say, is you have to work in a non-convex design space where there are lots of local optima. And the field of evolutionary algorithms is basically focused on that problem. What do you do if you get stuck? And I will have enough time to talk about the state-of-the-art algorithm that does a pretty good job of getting you unstuck. Doesn't guarantee it, but it does a very good job. I'll talk about that in a moment.
Thank you.
Okay, so moving ahead, back in 2014, who's now here on the faculty in computer science, did his PhD with Hod Lipson at Cornell. And at that time, Hod's group was perfecting or finishing their soft-bodied simulator, this VoxCAD simulator. So Nick connected an evolutionary algorithm to the VoxCAD simulator, and the result is what you see here. So in this case, Nick has made 4 basic building blocks available to the evolutionary algorithm: red and green voxels, which increase and decrease in antiphase to one another, like agonist and antagonistic muscle groups; cyan voxels, which are passive soft material, so skin or fat; and dark blue tissue, which is hard passive material like bone. You'll see in this case, again, this example that evolutionary algorithms typically find non-intuitive solutions, which is that basically the best thing to do if you're only rewarded for speed of travel is to produce a giant ball of muscle. Evolution basically discards the light blue and the dark blue voxels and comes up with something that works. Okay. As Luis was mentioning, however, the dirty little secret of evolutionary algorithms is that they tend to get trapped in local optima. So I'm going to talk about some of Nick's more recent work, which is on the evolutionary algorithm side, which is how to get evolutionary algorithms unstuck, which ended up helping with the xenobots project. So here's an example of an evolutionary run. So we have the number of generations of evolving populations of robots on the horizontal axis. And each colored pixel here represents an individual robot. The bands of color that you see, these are basically robots that are related to one another. So all the pink robots, green robots, and so on. You can see that after about 100 generations, there was no further evolutionary improvement for 6,900 generations. This was a couple of weeks running on NASA's Pleiades supercomputer, which back in the day was one of the most powerful supercomputers on the planet. So it was a little embarrassing for us that we wasted a lot of compute on the Pleiades cluster because the evolutionary algorithm got trapped in a local optimum. So I'm going to walk you through a really neat idea of Nick's, which is a twist on an evolutionary algorithm to help it gets unstuck, and it works as follows. We're going to assume that we're evolving robots, and we're going to assume that the mutation operators available to the evolutionary algorithm, the ways in which it can modify these evolving robots, is to either alter the physical structure of the robot, its morphology, or it's a mutation that alters the control policy of the robot. Imagine that we're imagine a hypothetical evolutionary algorithm where we're partway through the evolutionary process, and evolution has found this gray bipedal robot form with 2 legs. And the big arrow here represents about medium speed of travel. So imagine this hypothetical robot takes a couple of steps and then falls forward. So it gets some fitness for moving forward, but assuming we could find a coordinated bipedal gait, the robot would travel much further, much faster. Imagine that this robot produces a mutated copy of itself, which is the following. And if I go back and forth a little bit, you'll see that the mutation basically lengthens the legs of the robot, but does not make any change to the neural control policy of this robot, which is represented by the black circles and the arrows. So we basically evolutionarily changed the body, but not the brain of the robot. It's unlikely that this control policy knows how to orchestrate the movement of the robot with the longer legs. So this robot is likely to stumble earlier and fall over faster than its parent robot did, which means that it doesn't travel as far. If that's the case, the child gets lower fitness than the parent, and that child is probably going to be deleted from the population and lost. But from our privileged external perspective, we know that longer legs, at least for fast-legged locomotion, is probably a good thing. There is potential in this morphological innovation, but evolution might require some time to capitalize on that potential innovation. At the moment, from evolution's point of view, it's a bad idea. Imagine that this robot manages to stay in the population for one more generation, and it produces a grandchild, or it produces a child which is a grandchild of the original robot. This child has the longer legs of its parent, but this child incurs a second mutation, which is some change in the control policy, which alters the way that the legs move. And imagine that that change allows this grandchild robot to successfully coordinate the movement of its longer legs. So this grandchild will be able to move faster than not only its parent, but its grandparent. So Nick came up with this algorithm, which is basically this idea of morphological protection. In the evolutionary algorithm, when there's a change to the body, we're going to temporarily reduce selection pressure. There's going to be a greater likelihood that slower moving robots are kept around for a little while. But mutations to the control policy are not protected. I'm going to show you how this works. And the way that this works is to use a particular type of evolutionary algorithm called a multi-objective optimization method. So instead of one number, we have two numbers associated with each solution in the population. Let's imagine that on the vertical axis here, we're going to measure the fitness of each of these four hypothetical robots here. And I put 1 over fitness because we're going to try and minimize this axis here. On the horizontal axis here, we're going to label each robot with an age, which is not the age of the robot, it's the age of the lineage to which the robot belongs. We're going to assume that we're trying to minimize both objectives here, 1 over fitness and age. So we prefer younger solutions, and we prefer solutions that have a larger fitness. We are then going to visit each of these 4 points, and we're going to look for points that we're going to look for dominated points, which are points that are equal to or worse in both objectives compared to another point. You can see that these 3 red points are dominated by the green point. The green point is better, or at least equal age to the other 3, and it's more fit than these other 3. So we're going to delete the dominated solutions and leave only the remaining non-dominated solution. That's the end of the generation. We now age the only survivor. So the age of this individual, who is the only individual in a single lineage, has an age of 1. We now inject a new random robot into the population. This would be like an organism washing up onto the shore of an island. It's the first one of its kind on that island. So because it's younger, and in this case it's a random robot, it's probably unlikely to do as well as this partially evolved robot down here. So this new robot has an age of 0. It's the only member of its lineage, quote unquote, on the island. We have 2 remaining slots. We're assuming we have a population size of 4 here. We deleted 3 of the dominated solutions. We injected a new random individual. We have 2 remaining slots. We flip a coin. Heads, we choose this robot. Tails, we choose that robot. Produce a new individual. And in this case, we assume that this individual produced this child. They have the same age because they belong to the same lineage. This individual produced this child. You see that this child has slightly better fitness than its parent. This individual produced this child, which has the same age because it belongs to the same lineage, but it has a much worse fitness than its parent. In this case, these 2 individuals dominate these 2 individuals. We delete those and we repeat this process. In this case, we have these 2 survivors. We inject a new random individual onto the island. In this case, it just happens to actually do well by chance. And you can see that it's younger, it's further to the left, and it has higher fitness than these 2 individuals. So this one dominates both of these, and both of these would die off. Okay, this is a well-known evolutionary algorithm known as AFPO. Nick's morphological protection algorithm does the same thing, but it replaces this objective of age with a new objective, which is the number of generations since the robot suffered a morphological mutation. So it's a bit of a mouthful. So let me walk you through this idea. Let's imagine we have 1 individual in the population at the moment. This individual has this form that I've shown you before. It has this fitness. Imagine that this individual produces this child, which just suffered a morphological mutation. It's got longer legs than its parent. So the number of generations since the last morphological mutation is 0. Because it has this value of 0, you can see that this longer-legged child has worse fitness than its parent. This individual is higher in this plot than this individual is. In a traditional evolutionary algorithm, this individual would immediately be killed. But at this point in time, this individual is protected because although it's worse in fitness, it's younger. So we're going to give it the benefit of the doubt for a while. assume that this individual, now this parent here produces this child, which has the longer legs of the parent, but it also suffered a control policy mutation. We've changed the controller in this grandchild robot. And again, imagine that this control mutation allows the grandchild to orchestrate the movement of its longer legs. So not only does it have better fitness than its parent, it has better fitness than its grandparent. So in this way, we have an evolutionary algorithm that can temporarily reduce selection pressure on individuals that have recently have suffered recent changes to their physical structure. But as they start to produce children and age, that protection degrades over time. Last thing that's kind of interesting about this approach is that forgot what I was going to say. We're not introducing any additional hyperparameters. We don't have to tell the algorithm how long to keep these protected individuals around for. If we did, those number of generations that we keep something around for, that would be an additional hyperparameter. When you're building AI algorithms, you don't want to introduce too many knobs that you need to turn to get the algorithm to work well, where these knobs would be hyperparameters. Daniel, I think I have 3 minutes left until Q&A. Is that right?
Yeah, that's right. But
okay.
I think.
Okay. All right. So I'll just start to finish up here. So as I showed you before, this is what happens without this morphological protection idea, where the population of evolving robots gets trapped in a local optima. Here's what it looked like with Nick's morphological protection method. This was good use of NASA's Pleiades supercomputer. He ran this for several weeks, and even after 6,000 generations, you can see that the evolutionary algorithm is still coming up with faster and faster moving robots. The height of the points in this plot represent faster moving robots. You can also see that there are lineages, like this lineage of red robots here. In Nick's algorithm, all of the red points that make up this red curve, they all have exactly the same physical structure, but they all have different control policies. So same body, different brains. At this point in time, these red dinosaur robots, there was a blue mammal robot injected into the population. It had a different morphology from any that had been seen in the population so far. This initial blue robot moved much slower than the fast-moving red dinosaur robot. But these blue robots in this sequence here, this lineage, suffered a series of control policy mutations that exploited something about the body plan of these blue robots that allowed the later, the more evolved blue robots to move faster than the red robots. The blue robots at this point were faster and younger, and they killed off the red dinosaurs. So you see this turnover in the population where you can see here the red robots have converged on a local optima and gotten stuck. There's been many generations in which there's been no significant increase in speed in the population. They're sitting on that local optima where elsewhere in the search space, these blue robots are climbing the slope of another optima. And it's probably another local optima, but at least it's a local optima that has a higher peak than the original local optima. So in morphological protection, you have a population that's climbing in parallel multiple local peaks. They get stuck on those peaks, and any newer individuals that find other peaks and climb higher globally compared to the others knock them off their peaks, and search is focused more on those individuals on those higher local peaks. I think I've run out of time, so just maybe one last thing to talk about. One of the things that we explored in the xenobots project, I don't know if I don't know if Sam mentioned this when he talked to your group before. One of the reviewers of our PNAS paper said, why didn't you just use gradient descent methods or gradient estimation methods? So Sam compared his evolving green xenobots using an evolutionary algorithm against designing xenobots using state-of-the-art, or maybe not state-of-the-art, but very popular gradient descent methods. For very small designs like you see here, there's no difference. An evolutionary algorithm does just as, gradient descent methods do just as well as evolutionary algorithms. But when you move into larger design spaces with larger and more complex robots, evolution does much better. Part of the reason why is, in this case, we are searching. We're searching over parameters that are integers rather than floating points, and so it is not you're not able to differentiate and sense gradients in this search space. So there's another explanation, which I probably don't have time to go into today, about advantages of using evolutionary algorithms in non-differentiable non-differentiable search spaces. I think that's another kind of interesting thing to explore. So I think I will wrap up there. There's a link to the all things xenobots if you're interested. As I mentioned, we're moving forward along a lot of different lines. One line is trying to automatically build xenobots. At the moment, Doug, our microsurgeon, is building them almost cell by cell. We're looking at some bioprinting technologies to automatically manufacture xenobots. We're looking at allowing the evolutionary algorithm to incorporate new tissue types and sense organs and different types of actuators into the biobots. Some other things as well. This was all funded by DARPA, so thanks to the DoD, and thanks to all of you for attention. Happy to field a couple questions.
First of all, thank you so much.
Sure.
Yeah, I think
Thank
Dr.
you.
Lewis and Dr. Hammond, yeah. Take over. Ask a question.
Hello. I would say first, I mean, before either Hamid or myself ask the question, if the students have questions.
Yeah.
Yeah, there's no such thing as a dumb question. Happy to answer any questions you have.
All right. So let me just my question is really quick, I believe. So I'm very interested on when that thing about fitting the error right into the evolution.
Yes.
So this is something that we actually use, as you mentioned. We basically control people use that all of the time. There is this thing called the actor critic ensemble.
Yeah. Okay.
I was wondering. So I got fixated with the frog tissue moving and fitting the. So it was quite cool, actually. Very interesting. But I'm wondering. So that movement, the movement of the in vivo cells,
yep.
is that's open loop, right?
It's open loop in simulation. Whether it's open loop in the xenobot itself, it's hard to say. So this is obviously, a big departure from robotics. Is in a physical robot, you know exactly what component is talking to what other component.
Right.
But when you rearrange frog tissue or any biological tissue, those tissues are made up of cells, and those cells themselves are fantastically complex machines. With their own, sensing and actuation abilities and communication protocols and. So the cells in the xenobot are talking to one another, and we can't. I would be surprised if it's open loop control. There is probably some coordination going on among the rearranged tissues, but what that communication is currently unknown. And that's something else we want to investigate. Can you actually indirectly infer what that spontaneous organization is? So Jason was mentioning you would expect some entrainment among the muscle tissue. So does it occur? How often? What rearrangements favor or frustrate entrainment? Those kinds of things you could explore, I think, with this kind of technology and learn, not just make useful robots, but learn something about the fundamental biology here.
So in that front also, so this actor critic I mentioned, so it's basically, but you need to identify clearly here what is the input and what are the outputs, so that you can actually close the loop if you want in any way, right?
Yeah.
So in this particular case, what would those be?
Yeah, well, it's a partially observable problem. You don't know a lot of those inputs and outputs. one of the things we're exploring is imagine your fitness function is not speed of travel, but the fitness function is how well the xenobot advertises its internal function to whatever you're observing it with. So in the simplest case, you could get the AI to design the flattest self-moving xenobot, because something that's 2D is obviously easier to interrogate under a microscope than something that's 3D. So if you don't know what these inputs and outputs are, could you at least evolve something that advertises its internal function better than a wild type frog, which clearly doesn't give up its secrets very, very easily. So that's something else we're interested in exploring.
All right, thank you.
Yeah, Dr. Hamid, please go ahead.
All right. Thanks, Josh, for the great presentation. It's very interesting research.
Thank you.
So in the bipedal robot section, so you mentioned that you're evolving not just the physical structure of the robot, but also the algorithm that's controlling the joints. So I'm wondering if it makes more sense, or maybe this is a different way of looking at the problem, to look at it in a modular way, where hardware gets sort of evolved according to your evolutionary algorithm, but software gets adapted, as the robot learns to walk. So essentially, there's learning over generations, but also learning through time for each individual robot. And I'm asking that because in controls, things like bipedal robots, you can define either reinforcement learning for offline adaptation or something like iterative learning control for online adaptation as the robot keeps walking and learning from experiences.
Yep.
So I wanted to hear your thoughts about that.
Yeah, that is also the big question at the moment, is if it's worthwhile, if you can't presuppose the physical structure and you need to search for it, like with an evolutionary algorithm, how do you combine learning and evolution of physical structure? I have a couple students working on this. I know there's a couple other groups working on this, where in the outer loop you have an evolutionary algorithm, and in the inner loop you have, in our case, usually reinforcement learning. The problem, though, is what is the computational budget you give to reinforcement learning for a given morphology? And that is difficult, because if you're searching over thousands or millions of different morphologies, then if you're wasting your, if you're trying to do reinforcement learning on an unpromising body plan, you end up wasting a lot of computational effort. So, how do you estimate how much learning effort should be expended on a given design? That typically requires the introduction of at least one additional hyperparameter. And the morphological protection idea that I mentioned is one way to get rid of those hyperparameters. It's also obviously got other flaws, but I think that's kind of the holy grail, is how to balance, search for physical structure with search for optimal control.
That's a very good point. So maybe one way of addressing that would be if you know the physics of the system, everything is governed here, it seems, at least, by something like Newton-Euler equations.
Yes.
So when you're trying to learn the control policy, perhaps it makes sense to maybe invoke some of the physics when you're trying to learn the control policy.
Yeah.
Because then you're not searching over, arbitrary control policies. You can narrow down your controls to be sort of adapted to the physics in some clever way, and that might actually reduce your hyperspace, because now you have to optimize over maybe a bunch of constant parameters.
Yeah, that's a great point. We're working with a group at MIT who's built a physics engine called Tai Chi, and it's a differentiable physics engine. So we're working with them to see if you can actually backpropagate error into the physical structure, and then, like you say, it's one way of incorporating the physics into the training of not just the policy but the body. But I think that's a big ask. There's lots of different ways to do that, and I think it's a good question, good observation.
Very interesting. Thank you.
Thanks, Hamid.
I think we might have time for one more if somebody has a question, and then we will wrap up. Going once. I think there are no more.
Okay.
Thank you so much, Dr. Jason. I hope people. I really enjoyed your presentations.
No problem. Thanks so much for having me, and thanks for sticking around on a Friday afternoon. It's a pleasure to be here. Sure.
Okay. Thank you so much. Thank you so much. I do have just one question, but I think people can just leave and it's okay, no problem. Sure. So the question was, I think when you were talking about the xenobots, I'm pretty sure the xenobots don't have a brain, yeah. So they don't have processing information power, like what Dr. Lewis was going to mention.
They don't have a brain, that's for sure. Yeah. But you cannot conclude from that they don't have the ability to learn.
Oh, okay.
So there's a lot of very complex and rich bioelectric signaling among cells. And again, my colleague Mike Levin, this is what he's actually most well known for, is his efforts to crack the bioelectric code. Cells talk to one another using non-neural but electrical calcium signaling and all sorts of different signaling. And it seems likely that they learn from one another using that system. So
I think what Dr. Bates was alluding to, in a sense.
Yeah, I mean, I don't know if you would count entrainment as learning. Maybe. Again, learning is a loaded term, but yeah, I mean, where's the dividing line between entrainment, adaptation, learning? Again, this is something we'd like to do with the xenobots, is can you actually learn? Can you design an organoid or a synthetically designed piece of biological tissue where it's more easy to see how the cells speak with one another and what is it that they're saying?
Sounds difficult. But anyways, thank you so much, sir. Thank you so much.
No problem, Daniel. Have a good weekend, everyone.
Have a good weekend.
Bye-bye.
Thank you very much. Bye-bye.